So now we are entering into a different phase of control theory, the nonlinear systems. Whenever we talk about nonlinear systems, people are a bit afraid. But we will see that actually dealing with nonlinear systems is not at all difficult. We can extend almost the same theory which we are using for linear systems to nonlinear systems. This is one of my favorite subjects. Also, very much favorite subject, this nonlinear systems. So, first lecture, I will discuss the features of nonlinear system, the characteristic of nonlinear systems. Then we will study stability. Then in the third lecture, we will study steering mode controller. Tomorrow, we will study about the feedback linearizing controllers. Little bit. If you go to any textbook or any place, people will say all the systems are nonlinear to certain extent, right? They will say it is written there, right? What I want to say, the system is never a linear system or a nonlinear system. That point, please be clear. A system is a system only. System is a system. It is neither a linear system nor a nonlinear system. It is, if it behaves linearly, you can consider at that time it is a linear system. If it behaves nonlinearly, then it is a nonlinear system. Clear? I can give an analogy. We cannot say whether a person is good person or a bad person. It has nothing to do with the person itself. Right? If he behaves properly, then we say it good. If it behaves bad, right? But if you go, because you are all academics, and if you say that you ask the students the question that what is a nonlinear system, and their answer invariably throughout the world, you are going asking the question, the people will say a nonlinear system is that system where the principle of superposition does not hold good. It is not applicable, right? They will say, this is all students answer it. But that is partially correct. Even for the linear systems, principle of superposition also does not hold good. In the linear system, suppose a linear circuit, if you are calculating the voltage and current at different points, then you can apply the principle of superposition of multiple sources. We all have done it, right? For calculating the voltage and current, the principle of superposition holds good. But if you want to calculate the power, even for the linear circuit doesn't hold good. Because power is a quadratic function. Power is a quadratic function of resistance. Remember this thing, linear circuit, if you calculate the voltage or current at different points by multiple sources, for each source you calculate the current, then add them together, that's fine. But power, no. You cannot do it. So because power is a quadratic function of the variables, right? So even for linear systems also, the principle of superposition does not hold good while calculating a power relation, right? Just like I give an analogy, Amresh Puri is a typical Bollywood actor. When you talk the name of Amresh Puri, people think that he is a villain, right? Which is not true. Sometimes he has also acted character role, right? So you cannot demarcate the way he behaves, right? I'll give another example here. Very good example, all of us we give it. saturation nonlinearity. This is the phi I characteristic. We say it is nonlinear, right? But it's not, you cannot make a general statement like that. Because if you operate within this zone, when the current is less than this, system is linear. The moment you operate beyond that, then the nonlinearity sets in, right? So it all depends where your operating point is, how you are operating. That decides whether it will behave nonlinearly or linearly, right? So first point is important because the academics see system is system. There is nothing like linear system, nonlinear systems. It all depends on its behavior. Clear? Okay. First point is your principle of superposition doesn't hold good, but with this constant, very standard questions we ask, y is equal to mx plus c. Y is equal to mx plus c. Linear or non-linear? Linear, right? Apply principle of superposition here. You apply principle of superposition here. Y x1 will give you y1 is equal to mx1 plus c. x2, y2 is equal to mx2 plus c. Okay? x1 plus x2, x1 plus x2, what it will give? Can you add them together? If you add them together, it will be m into x1 plus x2 plus 2c, right? Which is not equal to y1 plus y2. So principle of superposition doesn't hold good for y is equal to mx plus c. Y is equal to mx plus c is not a linear. It is coming under the class of systems we will study tomorrow while doing with the feedback linearizing controller, affine class of systems. So mx plus c, remember, very standard academic questions. Y is equal to mx plus c is non-linear, right? That is not important. Stability we will discuss next lecture, so I am not emphasizing here. Linear system stability depends only on system parameters and not on initial conditions. But nonlinear system stability is different. We'll see. I'm not telling now. We'll see in next lecture. Why to waste time here? Important point is this point. Number 3 point is the most important point, which is not being emphasized in the nonlinear literature. Energy transfer takes place at a different frequencies. And that is a serious thing which I will tell you now. What is the meaning of that? The meaning is here, you see here. This is a square law nonlinearity, see here. You apply an input of sine omega t. The output will be a DC component and a 2 omega component. Do you see it? If you apply sine omega t here, there is a square law. So yt is equal to u square t, that is equal to a square sine square omega t. That is equal to a square by 2, 1 minus cosine 2 omega t. What is the frequency of that component, yt? What are the frequency of that component? One DC component and 2 omega component. Do you understand that? See here, this term, it has got a square by 2 into 1 minus cosine 2 omega t. What are the frequencies? One is constant, another is 2 omega, right? 0 and 2 omega, right? What is the input frequency? Input frequency is omega. Input frequency is omega. The output frequency is 0 and 2 omega. Square law, right? So energy transfer takes place at a different frequency. What is the meaning of that? If it's a linear system, I will elaborate this point shortly, 1 minute. If it's a linear system, you apply A sin omega t, you will get some magnitude, doesn't matter, B sin omega t plus minus phi. If omega is here, you will get omega, right? Nonlinear systems, no. Nonlinear systems, you apply omega, you may get some different frequency component, depending on the nature of the nonlinearity, right? Why it is so important? Why it is so important? I will tell you one example here. You know the oil rigs, ONGC here, Oil and Natural Gas Commission, ONGC, in the offshore oil exploration, there is oil rigs, right? The similar type of oil rigs in Europe, you will find above, they say North Sea, above Scotland, okay? And beyond that, there is quite a lot of oil rigs. They explore the oil. Okay. That is Norwegian government, they have got oil rigs there. This is the problem. I have not solved it. There is one student of Steve Billings who has solved it, and Steve has got that. That's very important observations. You see the rigs is there. Oil rigs, you have seen it. Oil in the structure, right? 4 cylindrical structures, cylinders, and this rig. Those people found that when the sea is very calm, there is no turbulence in the sea, okay, there is a severe vibration of the rig, which is, but whenever the sea is turbulent, there is no vibration. This is a real paradox, yes or no? This is quite paradox. When the sea is calm, absolutely calm, the wave is going at very slow rate, the rig vibrates. Whereas, when the sea is turbulent, there is no vibration. What is the reason? They collected data, wave force data, that wave is impinging on the rig structure, and they collected data, they found the model. I think Steve has done it, Steve Billings, my supervisor, with some student. You know why it's vibrating? They found the model between the wave force, okay, and the wave velocity, all these things. It is a nonlinear model. When the velocity, the sea is turbulent, okay, with that input, the resonant frequency changes from, say, I think about 0.7 hertz or a radian to 0.01 or 0.7. See, the resonant frequency changes because the model says 0.07. So when the resonant frequency changes to 0.07, so when the sea is calm, 0.07 means almost calm. See, you got a point, physical meaning. 0.07 radian means very low frequency oscillation. Sea is very calm. That input is impinged on the rig vibrates, because that coincides with the resonant frequency. Got a point? So usually you will find, if people are working on motor control, see here, like this. Suppose there is a cascade system, that is one system here, This is another system, system 2. This is another system, system 3. I'm just giving an example. This example is very important. Suppose you know the resonant frequency of this one and this one and this one. If you know the resonant frequency, what you will do? You will not excite the system at that frequency, right? Clear? Now, the problem is, you do not know which type of a nonlinear element is there in those systems, right? Suppose I know the resonant frequency here is omega 1, here it is omega 2, and here it is omega 3, right? I know it. So what I will do, I will not apply any input having frequency omega 1, omega 2, omega 3, right? So what I did, I apply a signal of frequency omega 4. If I apply a signal of omega 4, it does not coincide, it will not resonate, clear? But because of nonlinearity which I do not know, suppose this omega 4 is giving rise to some frequency. You see, suppose this omega 4 generating some frequency omega 2 and omega 3. Suppose, because just like I told you, omega is generating 0 and 2 omega, right? This omega 4 is generating omega 2 and omega 3. So these two systems will resonate. Got a point? So whenever there is a cascading system, this happens in the power electronics drives. Power ABB drives, it is driving these motors and the nonlinear device. You do not know which frequency is generated. If that frequency coincides, not necessarily resonance. If the frequency is very close to resonance, the amplitude will be high. Got my point? Resonance, there is no need of resonance to occur. If the frequency is very close to the resonant frequency, the amplitude of oscillations will be high. Right? So therefore, this energy transport takes place at different frequencies is a serious issue. It is really a serious issue. You must be very careful. And normally, in the academics, we don't emphasize on the energy transfer aspect, right? So this is the point. Now see here the cubic nonlinearity, again another example. I apply sine omega t, then I get sine omega t and I get a 3 omega t. I applied omega t, in the output is giving omega and 3 omega. Okay? Energy transfer takes place at different frequency. Right? Now you understand the physical meaning of that. What is the meaning of this? Is typical happens not only in we are human beings. You tell certain things to somebody. Have you seen the talk of the ladies? Not the ladies talk. Actually, we said ladies talk. Actually, it's not ladies talk. Everybody's talk. I will tell you, Sonny, you see, I am telling these things to you. Don't tell to anyone. Keep it with you. If by any means you tell someone that I am telling to you, don't tell to anyone, you will find within 5 minutes he will tell to everyone. He will tell others, okay, you see, Dr. Swami told these things to me and he told not to tell anyone what I am just telling to you, but you don't tell anyone. You got a point? This is the energy transfer. Takes place at different frequency. You see, you tell certain things. Then this fellow will transfer at different frequency, something then that fellow will transfer with certain, you got a point? I give in Odisha, there is a Paradip port in Odisha. So the question has come in the examination that in school, which day the Independence Day comes? So people say, one student has written August 15th. 15th in Odia language, I think Pandar. August Pandar. Pandar means 15. One fellow has written August Pandar. So another person, he copied it. But the ponder is not a term, he's pondered to Bandar, port. So he wrote, your Independence Day is August Bandar. The third person say, how August can be Bandar? It is Paradip Bandar. Now Independence Day is Paradip Bandar. You got a point? How this energy transport takes place at different frequency and it changes. Right? This is a typical characteristic of the system and you must be very careful about these things. Interchanging the cascading elements. In linear systems, if there is a cascading connection, you can interchange G1, G2, G2, G1. But it is not the case with a nonlinear system. You cannot just interchange this to that. Okay. Say, this, but this is not very important, but I will tell. Number 5 we will discuss after some time. Multiple isolated equilibrium points. I will discuss in today itself in this lecture. A nonlinear system, linear system has got only one equilibrium point. Remember, linear systems, no matter how complex it is, it has got only one equilibrium point. Again, repeating the point, linear systems has got only one equilibrium point. Linear systems cannot have multiple equilibrium points. Nonlinear systems can have multiple equilibrium points. Not that always it has got multiple equilibrium points. Okay. It can have multiple equilibrium points. Right? And multiple isolated equilibrium points. Okay, nonlinear system can have more than one isolated equilibrium point. This point it can have. You see, I am writing in the, see the wordings here. I am not saying that nonlinear system has multiple equilibrium points. Can have. There are nonlinear systems which has got only one equilibrium points. But most of the nonlinear systems has got multiple equilibrium points. And I will tell you what happens to these things later on. Today itself. Okay. Finite escape time means it can go to infinity within finite time. Whereas linear systems will go to infinity infinite time, but it has no meaning actually. That number 5, 6 point is a academic discussion because infinity is the 5 time constants I told you, engineering infinity. So, multiple isolated equilibrium points. It has, linear system has got one equilibrium point and nonlinear systems can have multiple equilibrium points. Limit cycle oscillation. This is important. Let us first understand why oscillations occur. Unless that understanding is clear, you cannot understand anything. Why oscillations occur? Remember, for oscillations to occur, no matter the linear system or any system, there must be exchange of energy. There must be exchange of energy. For oscillations to occur. This is a LC circuit. This is a LC circuit. Okay? Now, if you inject certain amount of energy either to the capacitor or to the inductor, right? And leave it free. There is no input here. You see, I am not applying any voltage here. Just apply the impulse input, inject some energy, leave it. There is no resistance here. So what will happen? Then the magnetic energy which is stored in the energy which is stored in the magnetic field of the inductor will be transferred to the capacitor electric field, and then because there is no loss, there is no resistance here, then it will again transfer to inductor. Okay? So this continues. Exchange of energy, the RL circuit will not oscillate. There must be exchange of energy, otherwise not. Right? Now here, what happens? Limit cycle oscillations. This oscillation is a bit different. This oscillation is different. To understand the oscillations, I will tell you one thing, which I tell it in different context. But this is India, I can utter those words here, because you can understand. Typical example of oscillations. Friendship. Who can become good friends? Chanakya has told these things. Exactly equal to the oscillations here. There are 6 characteristics. First is dodate pratighunnati. 2 people will be friends if you give something and he also gives something. You give him some present, gift, in his birthday, and he also gives you some present. That is exchange. I give, you give. Okay? Guhyamakhyati puchyati. You tell your secret to him and he also shares his secret. Then only you can become friend. Not that you will tell your secret and he will not say anything. No. Friendship will not last. Bhukte bhojayate chaiva. You ask him to come to a restaurant for dinner and he also calls you for dinner. You give him some food, treat him. These are 6 characteristics. This is a clear example of the exchange, you exchange. Okay? So oscillations to occur, similarly there must be exchange of energy. There must be exchange of energy. Then only oscillations will occur, otherwise not. Here, oscillations will occur because inductance exchange energy to capacitance, capacitance exchange. These type of oscillations in linear systems is different than the oscillations which I am going to talk, limit cycle oscillations. Limit cycle oscillations. Now first let us see what is happening. Then I will come back again. Dampers, damper windings, dampers in vehicles, okay? Suppose you drive in a good car and in the low variety car, you feel not comfortable. Why is that? Because you know the spring, the damper is not of good quality, so damping is there. Okay. Now let us see this equation first. Mx double dot plus bx square minus 1x dot plus kx is equal to 0. Let us see this equation, then we will discuss all these things. What is the damping? Damping, the usual equation is mx double dot plus bx dot plus kx, 0. The coefficient of x dot is the damping term, right? Coefficient of x dot is damping term. The coefficient of x dot here is b. The coefficient of x dot here is what? B into x square minus 1, right? So damping, usually what happens? It takes out energy. It takes out energy. Now if suppose x, the amplitude, displacement is less than 1. Suppose displacement is less than 1. If displacement is less than 1, what will happen? X square minus 1 minus. So that means negative damping. If x is less than 1, b into x square minus 1 is less than 0, right? Damping is negative. Usually damping is positive. or whatever you may say it, right? So, instead of taking out energy, it will put energy into the system. It will put energy into the system. So, the moment energy is put into the system, the amplitude of oscillation, see, a displacement will increase. Now, once it is increased beyond 1, it becomes positive. So, it will start taking out the energy. Got a point? So, sometimes you put energy, and the moment you put the energy, X will increase. Now, after that it increases, it will take out energy. You got a point? So, over a particular period, sometimes it is positive, sometimes it is negative, right? So, the effective damping will be 0. Let me tell you, what is the damping here? What is the damping here? Can you tell me? LC circuit, what is the damping? Damping is provided by resistance. Is there any resistance here? Damping is equal to 0. Damping is equal to 0, system oscillates. Okay? Now here, things is different. Sometimes the damping is positive, sometimes the damping is negative. The effective damping is 0. Okay? Effective damping is 0. So it will oscillate. Okay? But that's the difference. Damping is 0, pure oscillations. Effective damping is 0, limit cycle oscillations. Why that difference? You do not earn any money. You do not earn any money, your bank balance is 0. Case number 1. But you earn 2 lakhs and also you spend 2 lakhs. And your bank balance is 0. Are the same. From bank balance perspective, a person does not have any money, he doesn't earn anything, his bank balance is 0. Another person, he earns 1 lakh, spends 1 lakh, his bank balance is also 0. These two people are the same. One is a bloody beggar, another is a bloody scoundrel. He doesn't know how to manage his finance. 1 lakh, got a point? Two things are different completely. Limit cycle oscillation is like that. Effective damping is 0. Effective saving is 0. Effective saving is 0. Here saving is 0. Right? And another thing is there an input there? Is in this equation? Is there an input? Mx double dot bx square minus 1x dot plus kx is equal to 0. There is no input. Self-excited. Self-excited oscillations. Okay. What is self-excited? I will give an example. When my son was studying in school, I used to, on the way to university, I used to drop him in the school. Then nearby I parked my car. Parking is you cannot park anywhere in foreign countries. Your car will tow down, but there are lots of parking. I park a car and then I walk down. 2 kilometers I walk down to university. Every time, almost every time, while returning from the university, I come and I pick up the car and I come home. I found one particular person, I still remember that fellow, with the jean, with the different types of dress, a hippie type of dress. He will be just talking something. Just talking. Self-excited oscillations. Nobody is there. Nobody is there. Okay? It will be around say 4 o'clock or 3:30. I usually leave the university at that time. Okay? He will be talking. I always give this example to the students. I told her I parked my car in the Mount Eden Road and I found a person in the Kid Street coming and talking like this. Self-excited oscillations. The limit cycle oscillations. Got a point? So limit cycle oscillation is a very important phenomenon. And it occurs for a system, nonlinear systems. The characteristic is it is self-excited, no input is necessary. First point, there is no input necessary for the oscillations. And second point, the effective damping is 0. Sometimes damping is positive, sometimes damping is negative. Okay, clear? Very important phenomenon, limit cycle oscillations. And is different from the common oscillations in linear systems. LC circuit also oscillates, but that's different. We'll see today itself. No, that you cannot say. We have to determine by different ways. Standard ways you can determine. Otherwise, by analytically you cannot determine. Analytically you cannot determine the frequency of oscillations. Okay, we'll come to that point. We'll see how it will be. Chaos. Chaos, if this is the nonlinear system space, if you divide this is the entire system space is nonlinear, the chaotic systems will be this much. Very small percentage of nonlinear systems behave chaotic. Right? Very common thing, very common. We have seen it. PhD students, okay? You ask them, you perform this experiment or you do these things, and they will get some results and they will come. One of my students was there for mechanical, Leron. He is now in Melbourne. Leron was working some rotary inverted pendulum. One day he came to me and he told, Dr. Swami, I think my system is chaotic. I looked to him. What are you saying? What are you saying, Leron? How do you know it is chaotic? No, the response is looking such, it is chaotic. I will tell you, if a person comes to you as an academic and he tells you that I am doing some simulations, then I think it is chaotic, you tell him, you close your book, close your computer, go home or go to the Goa beach, then come tomorrow. System is not chaotic, you are a bloody idiot. Got a point? Anything, he is telling, it looks chaotic. What means it looks chaotic? What do you mean that it looks chaotic? Chaotic systems, don't take it, you see, the system, it appears to be random, but completely deterministic. You see the statement I am making here. Chaotic systems appears to be random, but completely deterministic. I will give an example, it will be clear. Suppose there is a agitation going on in the university. Suppose there is a student agitation going on in the university, and a group of students went to the Vice Chancellor asking them to you give us this thing, that thing, the examination has to be shifted. You give us all A+ grade, that is our demand. So we will not study, we will watch only television, YouTube. That is the agitation. Yesterday night in the hostel, group of 100 students, they made the plan that tomorrow we will go to the Vice Chancellor office and we will demand it, right? So the plan is there like this. This is the plan. Actually, we have made the plan yesterday that you will go, just give a push to the Vice Chancellor's door and enter. He will go and from the Vice Chancellor table, whatever file is there, he will throw it outside. He will go and scold the Vice Chancellor. This is all plan. And you people, you will go and stop the vehicles going to the university. All these things have been planned, meticulously planned, nobody knew it. Next day morning, you started doing it. You execute it. I am an outlooker, I am outside, so I will say, what is up? That is chaos. That is chaos. Appears to be random, but completely deterministic. Who is going to do what? It has been planned before. He is not going to push the door. You will do it. He is doing all this task has been assigned, right? All the task has been assigned. So I say chaotic system, that's your order in chaos. Order, got my point? That's your order in chaos. There is an order. So the student says that it appears to be random. No. First find the order. Chaotic system, and always remember, chaotic systems are not random systems. It appears to be random. It is not random. It is completely deterministic. It is completely deterministic. You can determine everything. Random phenomena you cannot determine. So chaotic systems is a bit different. It's a serious thing. Okay. Appears to be random, but completely deterministic, right? That's the order in the chaos. Another characteristic is extremely sensitive to initial conditions. Extremely sensitive to initial conditions. Got a point? Slight change, a very minute change, we said butterfly effect, I am not explaining that. It's minute change, the example is given as butterfly effect. That is the Amazon belt, that effect is if there is a butterfly affects the wings velocity, that will be a storm in the Indian Ocean. Okay, extremely sensitive to initial conditions, right? But the important point is, chaotic systems appear to be random, but it is deterministic. Another thing is, long-term prediction is not possible. It is deterministic. What is deterministic? The system whose behavior can be predicted precisely. That is deterministic system. A random system, you can do it. Here, prediction is possible, no doubt about that. But long-term prediction is not possible. I'll give an example here. Long-term prediction is not possible. Short-term prediction is possible. Weather forecast, that model is chaotic. Short-term prediction is possible. Suppose I predict the weather, what will happen tomorrow, it will be correct. Day after tomorrow, little wrong. Still day after, it will be almost wrong, right? So long-term prediction not possible, short-term prediction is possible because the model is chaotic. Okay. So and another point which we are not discussing here, chaotic systems, it requires a little bit of different mathematics. One is the fractal geometry. Fractal geometry. Have you heard the term of fractal geometry? Fractal geometry. Yeah, Mandelbrot said, yeah, fractal geometry. Yeah, yes. You see, the geometry which we study, and we know that we study, that is the Euclidean geometry. Euclidean geometry, but actually not the Euclidean geometry. This geometry has been developed by Brahmagupta. Now it is proved now. Okay, that is a different issue. There the dimensions are integer dimension. Dimension 1, dimension 2, dimension 3. But in the fractal geometry, we deal with the fractal dimensions. The dimension of something is 2.2, 2.4, 3.5. You got my point? Fractal dimension. So it is meaning is different. I am just giving only one example here. Okay, there is no pen here, that doesn't matter. Now see here. Suppose I have got a piece of paper. What is the dimension? 2. Now I make holes on the paper. I make few holes on the paper. What is the dimension? 2 are the same. A paper without any hole, paper with some holes are the same. They are not same. So how to distinguish this paper with that paper? Euclidean dimension cannot do it. So we have to calculate some fractal dimensions. Okay. Say for example, bread. You get different types of breads, right? So when these breads are produced, you can calculate the fractal dimensions of different breads. Then you will find which breads there are lots of porous things are there, right? So fractal dimension will distinguish these things. So I'll show you something today itself. So fractal geometry is being used to characterize some of the chaotic attractors. Okay. So only thing for you is, so important point to take it before I proceed further. Multiple isolated equilibrium points, energy transport takes place different frequency, limit cycle oscillations, and chaos, right? And chaos. Let's go further. Bifurcations. I am not into. See, chaos occurs. The system will bifurcate. System will bifurcate means like this. You understand this diagram? Do you understand what is the meaning of this diagram? First, this is not a time plot. This is the equilibrium plot. As one of the parameter changes, equilibrium. Now, okay, let me show you. You see here. See this equation, if this parameter R I am changing, you see here, just see the table. If R is equal to 1.9, the output is always 1, 1, 1, 1, 1, 1, 1, right? If R is equal to 1.9, there is only steady state value of 1, right? The moment the R changes to 2.2, now see how it looks. 2.2, 0.7462, 1.1628. Again 0.7462, 1.1628. Again 0.7462, 1.162. So it is in steady state, but two steady states, right? 1.7, 1.16, 0.7, 1.16, 0.7, 1.16. Okay? Period doubling bifurcation, that means two equilibrium points. Two equilibrium points. Now see, if the R changes to 2.48, now see, this one repeats again here, you see. It repeats again. Got my point? Period 4 bifurcations. Okay. So it goes to those, it is not transient. It repeats at certain points. Okay. Now see, this is called the bifurcation phenomena. The system enters into multiple equilibrium points. Okay? And that repeats. And if you plot, you see here, the response looks like this. And if you plot it, the equilibrium points, you see one equilibrium point until this point. Next, there are two equilibrium points. Next, there is 4 equilibrium points. Then there is 8 equilibrium points. Then system enters into chaos. System enters into chaos. These are the equilibrium point plots. Okay. You can see the graph, you can see it. Similarly, this Henan map, okay? So, now, yes. No, Henan map is the system, the different system. This is a different system also, here also bifurcation occurs here, you see there is a bifurcation here, there is bifurcation here. There is chaos here, and there is no chaotic here, you see. As the parameter changes, the things will change. Bifurcation says that if one of the parameter changes, how the equilibrium point changes. How the equilibrium points changes. We'll talk a little bit more about that shortly. How to analyze the nonlinear systems? There are different methods to analyze. One of them is the phase plane method, which I am going to show you now, because phase plane method. That particular method is only applicable for analyzing second order nonlinear systems, because it is a phase plane method. Plane means 2 dimension. It cannot be more than 2 dimension. So you take a nonlinear system or any system, you have 2 second order system. How many state variables will there? How many state variables? 2. So you just plot those, you get the response, you plot between x1 and x2 and see how it behaves, right? For a linear system, for linear second order system, if the poles are here, real axis, and if you plot the phase plot means you plot x1 versus x2. Not a time plot, remember, not a time plot. x1 versus, you get x1 versus time, x2 versus time, but you plot you give the command, plot x2, x1, no time. Then you will find in the x1, x2 plane or x2, x1 plane, maybe, it doesn't matter. If it is like this, depending on the initial conditions, it will look like this. The plot will look like this. So if the plot looks like this, you take a nonlinear system, then you get the response using ODE 45 and plot it. If it is like this, that means the system is stable, and right? If the system has got like this is one of the important, this point, complex conjugate eigenvalues. The phase plane portrait, it looks like this. No, you are not getting it. Now, see, I'm telling you, just bear with me. You have got a nonlinear system. You want to analyze what is its behavior, right? So what you do, you go to the computer, you get the response, x1, x2, right? You get x1 versus time, x2 versus time, right? But don't plot x1 versus time and x2 versus time. You get x1 and you get x2, then plot that x1 versus x2, right? If the system has got poles in the complex conjugate negative plot, then this phase plane portrait looks like this. Because unless, how do you interpret? Unless you know from known thing, how can you interpret? I will show you, this is a phase plane portrait. How do you know? Suppose somebody will show me, this is the phase plane portrait, then I will say, it is a damped oscillatory system. The oscillations, it's gradually, it is oscillating, oscillation amplitude is coming down, finally becoming 0. Complex, and this is called stable focus. It has got a name. We will say that the system at that equilibrium point behaves as a stable focus. That means you should know stable focus means the amplitude of oscillation is decreasing. Okay. Just like you see, you must know how a good people behave, how a bad people behave, how a criminal behaves, right? So if you know it, then I will show you the behavior of this system. A person is look like this. Then you know, okay, this one matches with an idiot. So that person is idiot. So similar like this. If there is a complex conjugate eigenvalues, the phase plane portrait is a spiral, decreasing spiral. Okay? I'm coming. Yes, yes, I understand. I understand. I understand. I got your point. Very good question. What is saying? This is the system, linear system. Okay. Now here also, the phase plane portrait, if you plot it, it will look like this, right? Another system, it is here, right? Here also, it will look like this, but how to know the difference, right? That you can know it, you see, it is coming down, coming down, coming down, right? So it will quickly come down. When it will quickly come, when the damping is more, if damping is less, it will slowly come down, right? Many spirals. What happened? So from that you can know it. Whether damping is more or damping is less. Damping is more means away from the geometric axis, sigma. Damping is less means closer, right? So from that you can know. This is just decreasing. Yeah, no damping, I'm coming to that. No, if there is no damping, then this is a circle. I'm coming to this point. A circle. Pure oscillations. Right. Pure oscillations, if there is no damping, and if you change the initial conditions, you will get another circle. Depending on the initial conditions, more right. Important point, which I'm going to talk now, any closed curve, any closed path in the phase plane indicates system is oscillating. Any closed path indicates there is oscillation. If that closed path is a perfect circle, it is oscillating almost sinusoidally. If it is instead of perfect circle, if the closed path is like this, let us say, then there is no perfect circle. The oscillations has got multiple frequencies, maybe superharmonics and subharmonics, all these things, right? Closed path in the phase plane analysis indicates there is no oscillation. Okay, we are coming to that point. There is that amplitude. No, frequency can find it. Frequency you have to do it some other analysis. See, the right hand side, the response, it is oscillating, the corresponding phase plane portrait. This is a time domain plot, this is these things. Here. Unstable system doesn't matter now. See, close. There is no, you see, all pure oscillations. This is pure oscillations. So this is almost circle or ellipse, doesn't matter. Now, saddle point. Saddle point means one side is positive, another side negative. So it's unstable. This point is important. Now see the difference. This is the Van der Pol oscillator. Limit cycle oscillation. This system exhibits limit cycle oscillations, right? Oscillations. Any oscillations means closed curve. Any oscillations means closed curve. Now see the closed curve here. It is not circular. Is it circular? This is some different shape, right? So it is a limit cycle oscillation. Right? And another point is, Isolated closed curve is a limit cycle. What is the meaning of isolated? Isolated means if there are poles here, then phase plane portrait for a particular initial condition, you simulate it with some initial conditions, you will get this one, right? You change the initial conditions little higher, you will get another circle like this. You change the initial conditions to another value, you will get another circle, right? So these circles are not isolated. By changing the initial conditions, you get different circles. Whereas here, by changing the initial condition, no matter what you do, there is only one circle. You see, I'm drawing it here. You start from this point. You come here. You start from this point. You change the initial conditions. You start from this point. It will not intersect, but I'm just showing here. It will again come to the same point. You start from this point. Again it will come to this point. Not isolated. This is isolated. It's not close, right? Only one closed curve in the phase plane portrait, right? 11.5, I will take only 5 minutes time to talk about the basin of attraction, then I will leave. Analysis part, see here, the interesting thing. Nonlinear systems, this is a very interesting phenomenon. Nonlinear systems can have multiple isolated equilibrium points, right? If a system has got multiple isolated equilibrium points, where it will converge, where it will go, because equilibrium points, if you have got 3 houses, one is Panji, another is near the airport, and another is in the NIT campus. If you have got one house, then you can come to that house only. If you have got multiple houses, where you will go? The system has got 3, see this particular system has got 3 equilibrium points. Okay, I will explain this diagram. When a system has got multiple equilibrium points, each equilibrium point has got a basin of attraction. I will give an analogy shortly. Each equilibrium point has got a basin of attraction, right? And if you are into that basin, you will be dragged into that equilibrium point. If you are operating in that basin, that means here you see, if the system initial conditions here, it will converge to this equilibrium point. If it is here, it is converged to this point. If it is here and here, this will converge to this point, right? Now see here, I will tell you like this. I will take this example, just you can remember it, okay? Suppose there is a particular person, he has got 3 mistresses. Okay, his wife is there at home and he has got 3 mistresses. Okay, so how many equilibrium points? 4 equilibrium points. The system has got 4 equilibrium points. His wife, mistress number 1, mistress number 2, mistress number 3. His wife lives in NIT Goa campus. Mistress lives, one in Panji, another is Ponda, another in Mupusar, there, right? 3 places. Now the question is, evening time he will go to some place. What is the basin of attraction? If he is driving and he is near to North Goa, he will not come here. He will be attracted to that mistress. The basin of attraction is here. You come here. You will enter there. If he is going to the beach there, near Panji, And the evening comes, it started raining. Basin of attraction of that mistress, he will enter into that. Got my point? So the basin of attraction will decide where you are and you will be pulled into that. You got my point? The wordings I am using it. If the system is there in the basin of attraction means that mistress will attract you, right, into that point. Right? So in chaotic systems, when you analyze, we always calculate the basin of attraction. It has to be done numerically, not analytically. It's difficult. Okay. It is not difficult. You see, I have calculated these things. I don't know whether I've given the program to you, but if it's there, I can pass it to you. It's not. I'm showing you the basin of attraction here. You see. Just a minute. Here. See. Basin of attraction. Huh? No, this system, I'll tell you, no. 2 pi 0 minus 2 pi 0, you see, I've done it, you see, this is 0, 0, minus 2 pi 0, plus 2 pi 0. But that is not the point. The question is, you see here, basin of attraction. This is if it operates in this zone, it will be attracted to that. If it operates in this zone, it will go here. If it operates in this zone, it will go there. Okay? Basin of attraction is extremely important. Clear? It has to be done numerically, not analytically. You have to find out the basin of attraction. No, these things I did it 20 years back in my computer, okay? I did not take all the initial conditions. I took some initial condition. It took 2-3 hours in my computer during that time. It takes time. But each initial condition, I will spread therefore it is coming. Otherwise, we can find out. So this is because of that. So we'll take a break now. And the next, any questions here? So nonlinear system analysis, 2 things you should remember. Principle of superposition doesn't hold good, that is okay. But even for linear systems also, principle of superposition doesn't hold good. You have to understand that difference. Energy transport takes place at different frequency. And don't say that it's chaotic. Chaotic is a different phenomenon altogether. You have to do many other analysis to check whether the system is chaotic or not. Right? And basin of attraction. If the system is chaotic especially, we have to be very careful what is the basin of attraction. So accordingly, we have to do it. Okay. Thank you very much. I will see in the next lecture the stability. So Professor Rahulkar will give how much time to you? 5 minutes, yes. Record stopped? Yes. So you're very strict, huh? Very strict master. So, I thought, no, the recording is stopped. I thought very strict master. 5 minutes only. No 6 minutes. Huh? Okay, we should start. Should we start now? Stability. If the performance of a particular student is not good, he is getting a D grade, lowest grade or something like that, university will accept him. He said, okay, your performance is not that good, but you can still come and study here. But if the student is a criminal, involved in all criminal activities, what the university will say? He is a student, is a very good, A+ student, but he is a criminal. University will say, you get rusticated from the university, right? We don't require this thing. We may require some bad performance students, but not criminals. Suppose one student has got some psychological aberrations, some mental problems, right? Depending on that, he is a mad fellow. Similarly, a system performance may be little bit poor, we can tolerate it. It's not an issue at all. But under any circumstances, the system must be stable. System must be stable. So this is the case for the last so many years. So many years means maybe 100, 200 years. People are talking a control system must be stable. Recently, with the introduction of the internet and network control system and the safety critical systems, not only the system should be stable, but system should be safe. Safety property and stability property, they are not necessarily related. A system is stable, not necessarily it is safe. A system is stable, is not necessarily it is safe. I am giving an example. Suppose you are cliff of a mountain, cliff, okay? Now, you stand, you see, we went to that day on that beach, which beach, Koberam or something like that, Kaberam, okay? So that beach, I see there are many young people, I mean the lovebirds, they are there and they were standing just on the cliff and taking photographs. I've seen it, I saw it. Stable, but is it safe? It's not safe. But a point. So stability and safety do not often go together, may not go together, okay? So the two properties are extremely important. System must be stable, right? What is stable? We all know. So just for the sake of, if you have got an equilibrium point, if the system, if there is an equilibrium point xc, if you slightly perturb from the equilibrium point, it must, whether it is returning to xc, remain close to xc, or diverge from xc, right? Got a point? Say for example, here, these diagrams you all know, so I'm just doing it for the sake of completeness. This is asymptotically stable. This is unstable. This is Lyapunov stable or neutral stable. If you just give the perturbation, it will go nearby and stay there. It will not neither diverge, these things, right? How to study the stability of a linear system? Linear system has got only one equilibrium point, first thing, it has got one equilibrium point. And that is stable if all the eigenvalues are in the left half plane, right? In the left half plane poles, system is stable. Right half plane poles, system is unstable. Imaginary axis pole, marginally stable, actually unstable. Marginally stable is an academic thing. It is an academic job. No marginal stability. Nobody will put you on the cliff of a mountain and you are marginally stable there. No, no, no. That is a practically unstable. So we say there is nothing like practically marginally stability does not exist. We cannot take that risk that we will ask the people to stand on the cliff because you are marginally stable. If something happens a little bit, you are gone, right? So marginal stable is an academic thing, I will tell you, but so system is stable or unstable, right? Left half of the S-plane, system is stable, right half of the S-plane, system is unstable. Now the question is how to study the stability of a nonlinear system, right? Nonlinear system analysis, even now people are doing like this. How they do it, I will tell you. They have got a nonlinear system, let us say x dot. They have got a nonlinear system, x dot is equal to fx u, nonlinear system. They find the equilibrium point. First point is find the equilibrium points. Equilibrium point or points, depending on whether the system has got multiple equilibrium points. Then they found the Jacobian, they compute the Jacobian matrix. Del F over del X, I am not putting U here. At each equilibrium point, X is equal to X star. They found the Jacobian matrix and then they compute the eigenvalues of this Jacobian matrix. Compute the eigenvalues of the Jacobian. See, why? 1 minute. Where it went? This is which lecture? Lecture 12, 11, no? 11 lecture, no, lecture 10. Okay. Wait, is it coming? Yes. And compute the eigenvalues of the Jacobian. Compute the eigenvalues of the. What is happening here? 1 minute, let me open in PDF expert. Yes. Compute the eigenvalues of the Jacobian. Okay, compute the eigenvalues of the Jacobian. Then if the eigenvalues on the left half of the S-plane, system is stable. Right half of the S-plane, system is unstable, right? That is what people do it, analysis. You may laugh. The system is nonlinear and people are using this linear analysis. Each equilibrium point they found the Jacobian, they linearize the system, okay? Then develop the controller. Does it have any basis? Is there any justification to do like this? The answer is yes. What they are saying, they are not fool. Okay, they cannot be very genius, but they are not fools. It has all come from the Lyapunov's theory. Lyapunov has developed two methods. The first method says, what is the first method? I am telling the statement here. Compute the Jacobian matrix A of the system around the equilibrium point. Compute all eigenvalues of the matrix A. then the equilibrium point Xc of the nonlinear system is asymptotically stable if all eigenvalues of A are negative. Right? Lyapunov method. Unstable if any of the eigenvalues is positive. But if any of the eigenvalues lie on the j omega axis, inconclusive. You cannot say that equilibrium point is stable or unstable. Clear? This is the Lyapunov method. So that gives the validity, okay, to analyze the system by using the Jacobian linearization. This is called the Jacobian linearization. Tomorrow we will study feedback linearization. Two things are different. Okay? Jacobian linearization, what it does? That is a system, it is nonlinear, okay? And you go and tell him that I know that you are an idiot, but please don't move around. You just move in your own seat. Don't go further. That is how the system is allowed to operate within a small region, and then you do it. Jacobian linearization. Feedback linearization, which we will study tomorrow, if the system is nonlinear, you are a bloody idiot, get out. Go out of the class. Completely eliminated. No question of compromise. What my point? Jacobian linearization is a compromise. That the system is allowed to operate within a small region around the operating point. Okay? Feedback linearization, no. Remove it. System is nonlinear, remove it. Right? Okay. Lyapunov told that you have got a nonlinear system, you get the equilibrium point, find the Jacobian, compute the eigenvalues. If the eigenvalues are negative half, absolutely fine. If it is in the positive half, it is unstable. But if it is in the j omega axis, then my method will not work. You have to resort to some other method. Clear? And most of the cases in power system studies, the Jacobian matrix eigenvalues are negative. So therefore, that analysis is also valid. Okay? Asymptotically stable. Asymptotically stable, I will tell you, because you are all academics, so how you are going to teach to the students about asymptotic stability. Asymptotic means as the time tends to infinity, how the system will behave, right? This one, you perturb it, it will finally come to this point, right? Right? Say for example, if I draw like this, if you are here, and you go and go and go and go and finally you will come again to this point. Okay? When we were student, in class 8 I was studying, there was a poem, I did not find out actually now, that poem name is The Quest. I always give this example to explain the asymptotic stability, The Quest. This poem is being taught to us in class 8. I will tell you what is that. There is a mother and son. Father is not there. So they were living in a very nice house, okay, near the Miramara beach. In where? In Goa, Panji. Very nice place. They were staying together, the mother and son. Then one day the son told to his mother, Mom, I don't want to live here. I am getting bored. Very common term in nowadays the youngsters. We are bored. What is this bloody boredness? I don't understand. Anyhow, the mother told, why we are bored? This is a very nice beach. Huh? No, I want to go and find out a house, quest. Then mother finally told, okay, you go and find out a house, then we will shift there, right? Then the son went, you see, this is the house, this is the beach, house. The son, now he went in search of the house, okay? Then he searched and searched and searched. After 1 year, he returned. Then his mother asked, "Did you find the house?" He told, "Yes, I have found the house." What it is? It is here and here and here. Asymptotic stability. You see, goes from this point, move around, move around, move around, move around, and finally coming to the same point. Right? Got a point? This is a quest. This is a very nice song. It's being taught in, this is a clear example of the asymptotic stability. Right? So, if the eigenvalues on the left half of this plane, system is stable, asymptotically stable, right half unstable, these things. If it is not, then Lyapunov gave a different technique. What he did, I am giving the concept and then I will tell you the mathematical significance of that. Now you came to the lecture today with lots of compulsion because you have taken leave from your institute. Okay, and it is all recorded here by this video here. Are you taking any video of those people? You take the video of those people, they should be in trouble. I should not be always trouble. So their principal will see whether they are attending here or they are going to see the beach of Goa. Okay, these people in the GIAN people should listen to this. Okay, doesn't matter. You have come here. See, the concept is here, simple. You have come here. You have taken food in your hostel or in the hotel, right? As time progresses, you have already gathered some energy, right? By taking food. As time progresses, if your energy comes down, then you are stable. Because as the time progresses, if your energy goes, instead of coming down, it increases, then you are unstable. Just like your daughter, her daughter's energy I have seen 2 times. As the time comes down, then she becomes very angry. You see, unstable system. There is no energy, feeling hungry, but still shouting with the mother. No, I will not take this thing, I will not take this thing. You got a point? Unstable system. Clear example of unstable system. So, Lyapunov told, let us do one thing. I have got a system. Let us find out a function which is not exactly the energy of the system, but almost similar to the energy of the system, and analyze as time progresses that energy is decreasing or it is increasing. If it is decreasing, system is stable. If it is increasing, Lyapunov told, no, I cannot say anything. That we'll see. If it is decreasing, system is stable. That's all. Full stop. Full stop there. If it is increasing, no, you cannot say system is unstable. Some other things are there. Okay? So let us find a function and differentiate that particular function and check whether that function is decreasing. If it is decreasing, system is stable. Right? This is the Lyapunov method. So Lyapunov function is an energy function. Lyapunov function, that function which you will describe not the exact energy of the system, but energy-like function, right? So you find a Lyapunov function Vx, we say, x is the state variable, a function, the energy function or the Lyapunov function. Find v dot x. V dot x is the differentiation with respect to time. That is dvx over dx into dx over dt. That is equal to dvx over dx into x dot. Find v dot x. Get the energy function and differentiate it. If it is negative, system is stable, asymptotically stable. System is asymptotically stable. If V dot x is less than 0, V dot x is less than 0, system is stable. V dot x is less than is equal to 0. If the is equal to 0 is there, the system is Lyapunov stable. That is, it is not asymptotically stable. Okay? So for that analogy I gave you, it is not coming to Miramar beach, it is going to nearby another beach. It is remaining close. It is not going out of this space. Okay? System is Lyapunov stable. Okay. So you take a function Vx, differentiate the function and see whether it is negative. If it is negative, system is stable. Right? Clear? Okay. Let us do the function, energy function usually is a quadratic function or an even function. You remember one thing, Lyapunov function does not describe the energy of the system because you don't know the energy of the system. You take a function which can be used, which can be a possible candidate for the energy function. I will explain these things. This glass, a glass can be a possible candidate to store liquid. Got a point? I cannot take this iPad as a possible candidate to store liquid, right? So Lyapunov told, you take only that function. You are not restricted for that. You can take any function. You can take this glass or you can take another bowl. Okay? You can take a big bucket. That's fine. I have no problem. But don't take a plate. Because you describe the system, you take a function which is a possible candidate for energy. What is a possible candidate for energy? It is a quadratic function or an even function. X square, x to the power 4, x to the power 6, no excess q. No excess q, x to the power 5, right? They are not the possible candidate for energy functions, right? You take any functions of that order and then differentiate it and find out. We'll discuss these things. Let us take an example first and then we'll see. Then we'll come back. Then we'll come back. 1 minute. Let me take the example. See here. x1 dot is equal to x2, x2 dot is equal to minus 3, x2 minus x1q. You may try with the Lyapunov function 1 by 4 x1 to the power 4 half x2 square. It's a possible candidate for the energy function. Then differentiate these things. It is there in the handout, I'm not taking time. Now you differentiate it, v dot x is equal to minus 3 x2 square. Is negative or positive? x2 square is all positive, minus 3 x2 square is negative. So the system is asymptotically stable, right? You take a function which is a possible, again repeating the point, take a Lyapunov function is a possible candidate to describe the energy system. Not necessarily you should know these things. Okay. But it should be nonlinear. Yeah? Yeah, because the quarter, x cannot be a possible candidate. It will be x square only, x square 4, so it has to be nonlinear. It's energy function, so it's energy function. Now, okay, there is a catch here. What is the catch? You take a Lyapunov function, you differentiate it, then you check the sign of that function, whether it is less than 0 or it is not, right? Now, what you check? You check V dot x is less than 0 or not, right? How to check it? Simple system, you can check it. It's an inequality. This is not an equality. V dot x should be checked for negative definiteness, negative 0, right? So you have to solve an inequality, okay? V dot x is less than 0. How many solutions are there? There are many solutions. Suppose I will say, find out the value of x which is less than 5. Find the value of x which is less than 5. How many solutions are there? Tell me. How many solutions? Infinite number of solutions, there are many. Right? Now, when there are many solutions, you have to find out the feasible solution. LMI feasibility, feasible solutions. I'll give the feasible solutions. When we are studying in year 2, we have got a mechanical engineering design. During that time, the electrical students also study little bit of mechanical. We have got a friend, I'm not taking his name, he's no more there. He passed away. He's a very good friend. But don't take it seriously, okay? So, the teacher gave a design to design the spring of the, what is that? Truck spring. Spring of the truck, and you have to design a spring. All the loads, all these tensile stress, all these nonsense things I don't know. Any mechanical people are here? Okay, then I'm sorry. Then otherwise I would have used any language here. So mechanical people, you know, they use all this tensile stress, this stress, this stress. Using this mechanical civil people, as such you are stressed. And in their old talk and teaching also, they teach you stress. Oh dear. How can they use that term, stress? I don't know. Tensile stress, this stress. Then there's the stress from your wife. There's the child stress, my daughter's stress. How many stress? Anyhow. So that's the stress. So that fellow, I remember Dr. Patnaik was sitting there and we all designed. Feasible solution I'm telling. And he got an answer. He told, because I was the topper. I was the gold medalist there, but that doesn't matter. So I'm now completely useless. So he told, hey, Swai, you see my design. I did it. I told, means you have done the design. Okay, I've taken a name. Colonel means his name. You have done the good thing. Then one of my friends, he laughed. He told me, means you will get a slap. You know what happened? Truck spring design, he has got the answer, 3 kilometer length. 3 kilometer length, spring design of a truck. He went and showed Dr. Patnaik. Dr. Patnaik got that particular notebook, threw it to his face. You bloody idiot. You don't know your spring design you are making 3 kilometers. Is it feasible? The truck. See, feasible solution. You got a point? Feasible solution. When it's an inequality, when there are so many solutions, you must find out the feasible solution. It is not an easy task. So, V dot x is a matrix, and you will find a linear matrix inequality, that is LMI. How many people are working on LMI? LMI feasibility. Linear matrix inequality, there is a package in the MATLAB freely available, semi-definite programming, and there is one YALMIP package. It will solve the LMI problem, linear matrix inequality problem, and it will tell you, give you some solutions. Then up to you, you have to find out which one is the feasible solution, so that system is stable, right? So you get a function, differentiate it, right? And I will tell you, if you see the people working in the control theory, real control theory, I have got a couple of students who was working on mathematical control theory. One expression for V dot x, you know how much It will take 3 pages. I have got a paper in International Journal of Physics Systems. My one student in German aerospace now working in Chatura. He derived one v dot x, 3 page. V dot x, this, then he put it in the LMI, then got a feasible solution. I told Chatura, for publication purpose, you are doing it. Whether people use it, he also laughed. We are doing nonsense things sometimes, but we have to do it. There is no other way out. You will surprise. You take a system, you define a function, you take the derivative, then you put it in that LMI form, then put it in the SDP, it will give you the solution. It is not easy, right? In 1990, in International Journal of Control, there is a special issue came celebrating 100 years of Lyapunov theory, Alexander Mikhail Lyapunov. This Lyapunov theory is being used until now. There is no other theory has been developed to study the stability of a nonlinear system. I am telling you, until now, no other theory has been done. Lyapunov stability being used. So what is that? Take a function, differentiate it. It appears to be simple. Okay. Problem. Lyapunov stability is a sufficient condition. It is not a necessary condition. Lyapunov stability, which is being extensively used in the stability analysis of the by the entire engineering community, is a sufficient condition. It is not a necessary condition. What is that sufficient? If the Lyapunov study, you do it, and you found the system is stable, that's fine. But if you found that the system v dot x is not less than 0, that does not mean that system is unstable. See this point, v dot x is less than 0, is stable, that's fine. Now suppose v dot x is not equal to 0, this does not mean system is unstable. That means if you can find out some other Vx which will say that the system is stable. Right? Now I'm giving an example here. 1 minute. Yeah. No. The first method, you can always use the first method. You linearize the system, you find the Jacobian, then you find the eigenvalues. If the eigenvalues in the left half of the S-plane, system is stable, there is no need of finding the Vx. If the eigenvalues are on the j omega axis, then you have to resort to this particular formula. Good question. Now, I will not start with the first method. Those people who are not control specialists, they should start with the first method, because linearize the system and do it. Okay? Linearize the system and do it. Linearization of a system, which we will talk tomorrow, the feasibility. Linearization, Jacobian linearization. This is just like our Indian government is working. Appeasement. Not only Indian government, throughout the world, appeasement politics. A person is idiot, and you tell him, you are idiot or I am not throwing you out, you better behave a little bit, be within your certain range, you stay here. Okay? But feedback linearization, other type of techniques are if it is a linear or non-linear, remove it, completely remove it from the system. So Jacobian linearization is okay, no doubt about that. Now see here, I'm saying this example here. This example, is it? Now this example, I'm just showing the result. 1 minute. This one is plus minus J1, not J1, that's typo. Now here, this particular system, I found the usual first method. I got the Jacobian, I got the eigenvalues of the system, and the system eigenvalues are plus minus J1. So now I cannot use the first method. So we use the other method and then we found out, okay. Actually this particular line is also wrong. I just show it for the students, I do it, I should remove it. A minus B x1 square x2 square. So if A is less than B, system is stable. If A is greater than B, that I have written it for the students' sake, actually I should not write it. Nothing can be done. If A is less than B, system is stable. That's all, full stop. Lyapunov has got the stability criteria. Lyapunov did not give any instability criteria. Remember, Lyapunov stability criteria. Lyapunov did not give any instability criteria. Under what condition, if V dot x will be greater than 0, system will be unstable? No, that criteria is not there. Okay, this line I wrote it because for the students who say that V dot x is greater than 0, avoid it, but this is not true. The first one, Lyapunov said you get a Lyapunov function and differentiate, if negative, system is stable, full stop. If your system is positive, nothing can be concluded. Now I'm giving the interesting point here. This system, I took a Lyapunov function, you see here, I took a Lyapunov function, this one, and took the derivative. Now this one, this is inconclusive, yet minus x1 qx2. So whether it is negative or positive, you don't know. Whether positive or negative, you do not know. So Lyapunov, using this function, it is inconclusive. System is same. I change the Lyapunov function. Then it is conclusive now. Same system. Right? So Lyapunov function, if it is negative, system is stable. If it is not negative, you keep mum. Nothing can be told. Right? Nothing can be told about the stability of the system. That is the problem with the Lyapunov function theorem. There is no method how to find out the suitable Lyapunov function. Although people give some methods, but having said that, although theoretically we say that we cannot find the Lyapunov functions, but now most cases, around 99.9% cases we found out. Usually the Lyapunov function is x transpose px, E transpose p. Usually we find out all the cases we have been doing. Which one? No. Here is the equilibrium point. Here is telling for the all things, all cases. But in other cases for each of the equilibrium points. I'm giving an example here. Suppose I have got a nonlinear system. I'm giving the let us ask me like this. Now this system has got one equilibrium point here, another equilibrium point here, another equilibrium point here, 3 equilibrium points. This is the stability boundary, stability surface. Now this is equilibrium point 1, E1, this is E2, and this is E3, right? I have got the system x dot is equal to Fx, right? Now I found the Jacobian matrix GA is equal to del F over del X, right? Now very clear Jacobian function matrix del F over del X at E1 will have got eigenvalues where? Right up or left up? Huh? Right up, because this point is unstable. You see, this equilibrium point is unstable, yes or no? This equilibrium point is unstable. So if this equilibrium point is unstable, it is obvious. So the Jacobian matrix here will have eigenvalues in the right half of this plane. This or the other equilibrium point here, where it went, I don't know. This equilibrium point, this equilibrium point, this equilibrium point. E1, E2, E3. E2, if you find the Jacobian matrix, E2 is stable or unstable? Stable. So this Jacobian matrix, so eigenvalue will be in the left half. And whereas E3, eigenvalues will be in the right half. Right? So this is how people analyze it. And this justifies, this particular theorem justifies the linearization analysis of nonlinear systems. Okay. If someone asks you that why you are analyzing, linearizing the system, you always cite the Lyapunov first method here. Because that justifies that this point. Any questions on this? The problem is there is no method how to find out the Lyapunov functions, but having said that, I'll tell you, usually we find out. Okay. There are many things have been developed nowadays. Lyapunov functions, because last so many years people are working on that. Linear matrix inequality, semi-definite programming, bilinear matrix inequality, sum of squares methods. These things have been developed in recent years to study the stability of the system, basically, essentially, using the Lyapunov method, right? You see, the problem is, I'll tell you, important thing you should understand, you can find out the Lyapunov function which can ensure the system is stable, but that is not a solution. You have to find out the boundary where it is entering into instability. Conservative result, non-conservative result. What is the meaning of that? I will tell you. A ship, this is the point, a ship is safe in the harbor. No problem. A ship is safe in the harbor. But that doesn't mean the ship should not sail, because that is the purpose which it has been built. Right? So you study the Lyapunov stability, you say if the ship is within this harbor, it is stable. That's fine. But what's the point? You find out, you just take the ship little away from the port and see whether it is stable or not. Still further, whether it is stable or not. Still further, you see, this is the point I am saying. This is the space. Lyapunov stability is stable. Is it stable here? Is it stable here? Is it stable here? Is it stable here? Okay, don't make it conservative. Okay, if you are inside the house, no problem of any accident. But there is no purpose for which you are built, right? So that is a conservative. So while doing research, people will say, using this Lyapunov function, I found that if the system operates within this region, it is stable. Using another Lyapunov function, I found the system is stable here. So naturally, this one is better. Conservativeness, you know, it is not conservative, a little bit expanding. No, that you have to do by trial and error. You see. Just increase it, just increase it. Yeah, the region will change. Region will change. No, the question is, I'll tell you like this. Questions are very good. It has got beautiful answers here also. All these problems lie with the Lyapunov condition is sufficient condition, right? Now, you have got a weapon. You have got a weapon, right? How many people you can kill? It all depends on many factors. First thing, how many people are there? How long the weapon is there? Okay? So depending if you change the weapon, then you can do many other things, right? So similar thing, different Lyapunov functions will give you different results. Different Lyapunov function will give you different results. So nothing is conclusive. So in the research, what we do, we found out that this particular fellow is using this Lyapunov function and it is showing the system is stable if it is remaining within this region. Then we define another Lyapunov function and we show that system is stable beyond that. Then, yeah, it is better. And then somebody, another third person will come, he will say, no, another Lyapunov function, they will show conservativeness, the conclusion conservativeness. My controller, my Lyapunov function is less conservative. So that's the point. No, that thing in the first method. Yeah. It will talk about the entire system, nonlinear system. It has nothing to do with the equilibrium points now. No, we don't say about that. We don't say about that. Second method, we are straight away doing it. We whole system. Very difficult, very difficult. Now, say for example, minus 3x2 square. B dot x is minus 3x2 square. So that x2, where it is doesn't matter. Be x2 square, it will be always be negative. That's the point. So the question is, if, okay, I'll tell you. If the system is completely stable, if the system is complete, that is the theorem says, if the system is actually stable, fully stable, no matter where the equilibrium points are there, then there exists a suitable Lyapunov function somewhere in the universe. That is the theorem. If the system is stable, there exists a Lyapunov function. No. You take a Lyapunov function and you find the stability. That's fine. Now suppose your Lyapunov function did not find the stability condition. So you don't say the system is unstable. You say that I cannot find out a suitable Lyapunov function. You can find out, you can search for some new Lyapunov function which may prove the system is stable. Because remember, Lyapunov is not in instability condition. There is no instability condition. Yes. They are not saying that. They say that if the system is stable, there exists a Lyapunov function. How to find out if that you have to search? So therefore, he is not giving any instability condition. But one thing is sure, if you prove it is stable, then it is stable. If you prove it is stable, it's stable. We'll give a break for tea, break, then we'll study about sliding mode controller. Any questions on lap no stability? Are you getting something on lap no stability, or this is forcibly put on you? Little, some ideas? Some ideas there, that's fine. At least you say that you get something, so I will be happy. Even if you say that I am talking nonsense. How to study? Then they found the Jacobian, they compute limit cycle oscillation. This is important. Stabilizability of the linear systems. I can talk offline. Oh, yeah. Controllers. Sliding mode controller. All the controllers which you are going to study in this course are very powerful controllers. Even our students are also doing the same thing nowadays, SMC. Okay? I will come to the concept here, why you are using it. In practice, just let's read it now, then we'll go. In practice, the models used for model-based controller design will be imprecise. There will be some error in the modeling. This may arise from unknown external disturbance, unknown plant parameters, and parasitic model dynamics. Design of a controller which provides the desired performance of the closed-loop system in the presence of these disturbances is a challenging task. Right? Models will have some uncertainty, always, right? So the question is, we have to design a controller which should work, even if there is some uncertainty, which because uncertainty you cannot avoid it. There are so many possibilities. What are the possibilities? Robust control. Robust control, it assumes the amount of disturbance bound. If the disturbance bound is given, then it can perform fine, absolutely fine, robust control. Adaptive control is one of them. Robust control, always remember, there is another misconception. There is nothing like robust control. Always remember these things. There is nothing like robust control. A controller which has got the robust properties is a robust control. Up to what degree that robustness is there, that depends, will define, right? So, robust control, there is nothing like robust control. Although we say roughly that this is the robust control design, mixed sensitivity design, mixed integer programming design, that's fine. But essentially, there is nothing like robust control. We have to see whether that control is robust or not. Sliding mode controller is one of the robust controller. What is that? I'll explain these things here. Very powerful controller, no doubt. Just I'm reading the slides now, then we'll see. The sliding mode controller is a robust nonlinear control technique that forces a system state to reach and remain on a predefined surface called the sliding surface using a discontinuous control law. There are so many things I'm telling here. Many things are there in this slide. This controller is a robust controller. That means it has got some robust property. It is a nonlinear control technique. The control law is not linear. U is equal to minus kx is a linear. Is not linear. It is nonlinear law. Its system state to reach and remain on the predefined surface. You cannot understand. I will give an analogy shortly. Then things will be clear. Why it is not coming? Why not writing? Yes. Using a discontinuous control law. Let us understand the concept of sliding mode control nicely with an analogy, then only mathematics will follow. All of you, few minutes before, were in the corridor, right? Creating sound, noise. All of you, including me, right? Then Professor Rahul Kaur, what he thought, that these people are bloody idiots. As long as they will remain in the corridor, as long as they will remain in the corridor, they will create noise. Let us do one thing. Push these idiots into this room. Push these people, you see, that's exactly what we are going to do. Not in the corridor, push these people into this room, and he knows the moment we are in this room, we cannot go anywhere. Clear? This is exactly sliding motor controller. This is exactly sliding motor controller. He knows because this is the sliding surface. So you have to push it by a control law here. Right? So because he knows, not only that, you see how it becomes robust. Mathematically we can prove it. Once you are here, nothing can happen to you because all protection has been taken care of. Okay, if you are outside, then nobody takes care of you. That's the point. You have heard the story of Duryodhana. After the end of the Mahabharata war, not exactly end, when Duryodhana was not killed, he went to the Brahma Sarovar. Brahma Sarovar is the sliding surface. Because as long as he is there, nothing can disturb, neither the Lord Sri Krishna also. It's very difficult. That's the robustness. Once it is there, he there in the mother's lap, no force in the entire universe can disturb him. Lord Sri Krishna knew it. He is in the sliding surface. He is there. So to kill him, he has to be pulled from the sliding surface and applied it here. Kill him. Got my point? So the question is, you see, by hook or by crook, so suppose there is a child. He is moving here and there. By hook and by crook, if the child enters into the mother's lap, it is difficult. Your job is, if you want to make the child safe, you push him to the mother's lap. When the child is in the mother's lap, it is very difficult to take him out. Got my point? Exactly the same thing here. Sliding motor controller is like this. When V.I. Utkin found out this sliding motor controller, God given him this particular thing, he told that there exist certain places, if we just put him there, then no matter what happens, nothing can happen. Okay? You understand the concept here? So, sliding motor controller, now suppose, first thing is you decide what you want to do about the system. Suppose I suppose that two examples I am giving. I know that if you will enter into a good restaurant, you will drink alcohol, you will make merry, then you are happy. I know it. Suppose my objective is you should be happy by drinking alcohol. Okay? So what I will do? I will make a control law who will put you into that hotel. Now suppose I want, instead of drinking alcohol, you should go to a spiritual function where there is a great sadhu is giving a discourse. That is my objective. So then what I will do? I will also push you not to the restaurant, but I will to that particular congregation. Got my point? So you decide, first you decide where you want to put the people. System should be sliding where? First, this design of the sliding surface. First you design the sliding surface, where you should go. Got my point? That is called designing of the sliding surface. Whether you will come to the restaurant, you will go to a film hall, you will go to the beach. Okay, first you decide. Okay, design of the sliding surface. Then once I decide that I will put you people there, then I have to find out a vehicle. You are here. I want that you should go to the beach, dance it. So I must make some arrangement that you should go there. Otherwise, how can you go from this place? right? So there is a reaching phase. You see, sliding surface is there in that mountain. There I want you to put. So then I will make a control law which will push you from this place and go there. And once you go there, I close everything. You are there. Nothing. Now then you cannot come. Now you cannot come. So design the sliding surface. First point is design the sliding surface. Then find out a reaching law, a control law, which will make you to reach there. To reach there. And once you reach there, in the sliding surface, you are robust. Understand the concept? Sliding surface design, reaching law. I decide to put you in Mars. I decided, that is my objective. I am getting money from GIAN, good hotels, staying, getting good food, nice treatment here. So I decide I am very happy, I will want to put you in Mars. Can I put you in Mars? I design a, so note that always the reaching law exists. You can, surface is Mars, but for that reaching law, reaching condition has to be satisfied. You should be able to reach there. You should be able to reach there. Not that always it is possible. Otherwise, anybody can put the system in any place, right? So design a sliding surface. Find out that it is possible to find a control law which can drive the system to reach there. That is not possible for all cases, just like I told you. It is not possible to put you in the Mars, right? Then system becomes robust, right? Yeah, sliding surface. Yeah. Yeah, sliding surface, yeah. But sliding surface is up to you. That's the design criteria. Whether it will reach there or not, that depends on the system condition. There are conditions. Got a point? Sliding surface you can design, but whether you can reach there or not, that depends there. Okay. Step 1, design the sliding surface. Where you will put it, right? Whether in the beach or in the hotels or in the cinema hall, what is the sliding surface? Because where you will slide. Okay. Design the sliding surface, sigma x is equal to x is the state variable. Define the sliding surface that the system trajectory will reach and stay on. This surface shapes the desired closed loop dynamics. Right? What you want, that will be there. Now, the dynamics on the sliding surface should be asymptotically stable, okay? And it should be reachable. Just like I told Mars, you cannot reach. Mars, you cannot reach, okay? So the system must be stable in the sliding surface. This is the condition. And that's the reachability. You should reach there. Just to change this thing. So why? Okay, that's fine. Reachable. You should be able to reach there, right? Suppose you will say, I want to my sliding surface in your sun. You are not Lord Hanuman that you can reach there. Is not reachable. It's reachable, the condition is not satisfied. Right? It must be possible to bring the system from any initial condition to this surface in finite time using a control law. That's a finite time condition of reachability. You say it is reachable. Auckland is reachable from Goa. Yes, it is reachable. Reachable, you will reach it by walking. You made a controller by walking, so you will reach after 20 years. Got a point? So we should define a sliding surface. It must be reachable in finite time. Because if it will reach after large time, there is no meaning, right? So these are the conditions. Stability, it should be stable, it should be reachable. Because remember, once you are in a sliding surface, all problems over. The modeling uncertainty, everything, system will be robust. No input constants. I understand what you say. No input constants, no. No input constants. That's a good thing, yeah. Once the sliding surface is defined, the next task is to design a variable structure controller that ensures all system trajectory reach the sliding surface in finite time. Once on the surface, the system remains confined to it. That we have to see. Now, variable structure controller is a wide, sliding mode controller is a subset of the variable structure controller. Because I am coming to that point, variable structure controller. Sliding mode controller is also a variable structure controller, but variable structure controller is not necessarily a sliding mode controller. Structure of the controller is variable. I will explain you what is that. I will give you an. Have you seen the young people or the elder people playing with the children? Suppose you hide and seek, or you are here, and you ask a child, you catch hold of me. Now see here. So what you did, you move. The child is the controller, or you are the controller, so the child is following you. Now suddenly you make a change. The moment you suddenly make the change, there is no finite trajectory. There is no finite trajectory. He doesn't know which trajectory he will take. Otherwise, he can design a simple controller so that he can follow you. He doesn't know what the finite trajectory. So what he will do, depending on how you change, he will change. Right? So similarly, if you change the control law, then what happens, the system behavior sometimes is oscillatory, sometimes damped oscillatory. You see, depending on the control law. This is the control how you are going there. Yeah, yes. Sliding surface. Yeah. You have PI controller. Yes, PI controller. Yes. Each structure go on changing. Yes, that's the point. The problem is, see the analogy will explain. Otherwise, mathematics is simple. You design the sliding surface. The theorem says if you are in a sliding surface, you are safe. You are safe. Okay. So I know that if you are coming to this room, you are safe. So you are in the hostel. I know that you are coming to this place, you are safe. So I am making a control law which will bringing from the hostel to this place. The problem is, you must come from the hostel to this place. In between, there is no guarantee what will happen. So the reaching phase should be as quick as possible. Because in the reaching phase, there might be some problem. We cannot ensure anything. Suppose you are coming to a hostel, you are safe here. But while coming by bus, you don't know whether the bus will break down or something. That guarantee I cannot take. In the reaching phase, when the system is coming from that initial state to the sliding surface, no guarantee. So we say finite time convergence to the sliding surface, finite time, and that time should be as quick as possible. Because no robustness, nothing. Nothing is guaranteed. Nothing is guaranteed. Just like insurance policy. If you do the insurance policy from tomorrow, insurance will take care. But from today until tomorrow, insurance is not going to take. Which insurance says that your insurance is from tomorrow. If you are in a sliding surface, I will take care. How to come to the sliding surface, that is your job. Got my point? No. No, yeah, that we are coming that. No, that is depends, but always reaching condition not satisfied. That you can design any sliding law, sigma x is equal to 0. The reaching condition says sigma x into sigma dot x should be less than 0. And sigma dot x depends on the system dynamics. You may not reach there. The control input in the sliding mode controller essentially consists of two things. One is called the equivalent controller. Another is a nonlinear controller. Okay? What is that? I will tell you like this. This is the sliding surface. This room is the sliding surface, right? You are outside. Now I am pushing you to come to this surface, right? But usually, just like human beings, the system states will not always remain here. I am asking you, say the very common thing, I will ask you all, go to your place, go to your place, go to your place, right? Now, somebody is standing on the door, and he will be looking whether you are in the room or you are outside the room. Usually, for some people here, they will not be here. They will try to go out of this. The moment they try to go out, that fellow standing there will push him. That is the nonlinear controller, this component. That is a switching law. If you go that side, it will push it. The two people I will put it. That door, two doors are there. If this is the sliding surface, so this controller will push you here. If you will always do oscillate here, because you are this is the nonlinear controller will always push you. You go here. The nonlinear controller. Okay, so that particular switching law component is this one. And when you are here, the controller which is there, that is equivalent. Yes. No, not always. Yes. Yeah. That's right. Yeah. The two components, one is equivalent control, keeps the system trajectory on the sliding surface once it has reached it, derived by forcing sigma dot x is equal to 0 under ideal sliding conditions, represents the continuous part of the control, this one. This nonlinear part drives the trajectory towards the sliding surface. So if you are just outside, little bit outside, it will push it. It drives. From any initial condition, typically discontinuous, and uses sign of the switching function. Right? What I want to say here, another thing. Any switching function, anything where you do the switching, there will be switching harmonics, switching transients. Okay? So the system becomes maybe a linear system, but due to switching it becomes nonlinear. Right? And when it becomes nonlinear, you do not know what sort of frequency it will generate. Right? One point I forgot to tell you at the beginning in the morning lecture. In signal processing, in filtering, we have been taught if there is a noise signal, you design a filter. It will filter it out. That's clear. Obviously, no problem. If the signal bandwidth and the noise bandwidth, they are separate, then you can use a filter. Signal bandwidth and noise bandwidth. But if they overlap, then by filtering the noise, then also filter the signal which is not desirable, right? So these type of things, normally what we do in power electronics, those people who are working in power electronics, they know. We have been taught a signal FFT can be approximated by a Fourier spectrum consisting of sines and cosines, right? And there those components are superharmonics. We say superharmonics. FFT is called F0, this is the component, sine omega t, sine 2 omega t, sine 3 omega t, sine superharmonics. Nonlinear systems can generate subharmonics. If it is superharmonics, that's fine. You can use a easy filter. If the subharmonics, that techniques are there, no doubt. Professor Veera Kumar knows it. The filtering techniques, they are the experts on that. I'm not saying that it's not possible, but you must be careful whether it is superharmonic or it is subharmonic. There might be some intermodulation. Suppose your system is excited by omega 1 and omega 2, the generation frequency omega 1 plus omega 2, omega 1 minus omega 2, omega 1 plus minus 2 omega 2, omega 1 plus minus minus. You see, there are many complex frequencies will generate it. And the switching functions are the useless functions actually. You know what the switching functions? Switching people are always idiots. You know it or not? The way human beings behave, the system behaves exactly in a similar way. Today in this party, switching the another party. The next party, you know, switching. They are the useless people, right? So switching functions are dangerous things. Got a point? So sliding mode concept is clear. Is there any problem? First design a sliding surface, then see that it is possible to reach there. Reaching condition first thing. Before designing any control law, first see, design a sliding surface and see whether it is possible to reach there or not. Now, if it is possible to reach there, then you find out a control law. Right? The control law has got two components. First component is, once you reach here, inside this room, then there must be some facility, there must be a chair, there must be a table to sit here. Okay? That is the equivalent control law. This part will decide. And there will be some people, they are not used to be in this room, so I will keep those two people outside. So the moment you just go a little bit outside, they will push you. You'll be here. Right? The theory says, it is there, I am not proving it here. The theory says sliding mode is robust against matched uncertainty. This point I will explain you. Matched uncertainty, very carefully understand what the matched uncertainty. Not any sort of uncertainty. Matched uncertainty. What is matched uncertainty? Or matched disturbance. You can say matched disturbance, let's say. If the system is x state is equal to a linear system, let us say x plus bu. X dot is equal to Ax plus Bu, right? What is X dot is equal to Ax plus Bu? What is the meaning of that? X is the internal variables. Bu, you see here, this is the room. We are all state variables. That door is the B channel. That is through that the input signal comes. Got a point? The input signal comes from where? From that door. That is the B matrix. U comes through B. Through that particular door comes. Now, this particular thing, all the input signal comes to that door. Suppose the system is disturbed. Suppose the system is disturbed. That is the input. That is the system states. And that is a disturbance. That is a disturbance. So, X dot is equal to Ax plus Bu plus E into D. E into D. That disturbance is called a matched disturbance. Matched disturbance. If that disturbance also enters in by that door using the same path. If the disturbance comes from other side, sliding mode controller cannot work. System, it is robust against system disturbance, which is not exactly system disturbance, matched disturbance. That means your input comes in that door, just like suppose you have got a house, 3 doors are there, right? You come through one door, so any idiots who are coming through the front door, you can take care of that. If somebody is coming from other side, you cannot take care. Clear? Matched disturbance and unmatched disturbance. Matched disturbance means the same door where the input is coming, the disturbance, assuming that disturbance is also coming through the same door. But disturbance can come from other doors also. Got a point? You understand any doubt about matched uncertainty? Matched uncertainty means the analogy is clear. The door is the B matrix. The input is coming in that door. The during the no reaching phase nothing no. Yeah? No, all uncertainty should be matched uncertainty. All uncertainty should be matched on uncertainty. A plus delta A, X, so it will take care. That's all proof is there in the lecture handouts. Right? Any questions here? Because I'm not going to, there's some, today, what is that? Handouts in the assignment, I don't know what is there in today's assignment, but any questions? Understand the concept clear? Sliding mode controller, what it does. Okay, once you sliding mode, so one thing in the nonlinear system, I forgot to tell you during that time that superharmonic, subharmonic oscillations, intermodulations, okay, those things are always present. Always present. One interesting thing I'll tell you, and I'll close the lecture today. I think people who are teaching signal processing must be knowing that. On the frequency component, any function we are approximating usually at the beginning in the school level by Taylor series approximation. Have you seen it? A function f of t around a particular point can be approximated. See here, I'm writing it. Correct me if my expression is f of x at x is equal to x0 is equal to fx0 plus del f over del x at x is equal to x0 into x minus x0, right? Something like that. Other things I don't remember it, so it's a Taylor series expansion. higher order terms, right? Taylor series approximation. This will help you in teaching the students actually, what I'm saying. This approximation, we are using it and it has been used for many years. Month of December, very cold time in Paris. There is a guy who is not a mathematician. There is a person who is not a mathematician. He is an engineer, the son of a Christian parish. His father is a priest in some of the church. There is a mathematical conference where mathematicians were there, students of Laplace, Poisson, Leibniz, his students. Understand the scenario? I am telling you, for the academics, you have to explain to the students to make the things interesting. He told, first thing, those people who are mathematicians, they don't want to listen to this bloody fellow. He's an engineer. He knows nothing about mathematics. That is the view. He told, you see, you are telling me that a function f of t, you can approximate the function by a series. I have got another function. Okay? It can approximate a wider range of functions than the Taylor series. Then people asked, what? You are proposing a method which can approximate. He told that the Taylor series which you are using for approximating cannot approximate a discontinuous function. But my proposal is, it can approximate anything. There are some people who are students of Taylor also, subsequent students. They shouted, your knowledge on mathematics is big zero. Don't talk nonsense here. He told, I can show you now. I can tell you that any function in this entire cosmos can be approximated by a simple continuous time function, sines and cosines. Just powerful statement. Powerful statement in the month of December in Paris conference, mathematical conference. I have got a function which consists of only continuous time functions. It can approximate both continuous time function as well as discontinuous functions, and my series is nothing but sines and cosines. Again shout. How can continuous time functions added together can approximate a discontinuous function? That's the point. Right? And that is the series. That fellow is Jacques Fourier. Fourier series. He told any function in this cosmos can be approximated by sines and cosines. And he told one of the powerful method of his method is, see how it is coming from. He told that you are using a differentiation operator in the approximating. Del f over del x. And differentiation operator, I told you, division operation is a useless operation, right? He told, I don't use any differentiation, I use only integration. You cannot divide it because there is a possibility of division by zero. But addition by zero, what is that? You see, Fourier series, everything is integration. Right? When Jacques Fourier told these things in the mathematical conference in Paris, with lots of objection, people said it took around 50 years time to see that what Jacques Fourier told, that is correct. You got my point? So for teaching to the students, you can tell them this story, that how this Fourier series came into picture. A function can be approximated by sines and cosines, a continuous time thing. Okay. I will close it now. Okay. Our boss is telling means boss. No doubt. No, 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 no. Example would be there. Example is there. No doubt of that. I'm adjusting. Yeah. No, no, absolutely fine. This is the proof I'm giving. This is the proof given. Example is last. Robustness proof. Example is here. X dot is equal to x plus bu plus dt. System is disturbance. Let us define the switching surface sigma x is equal to x. Now, you want a control law. It has got two parts. One is the equivalent, you see, ut is equal to one linear part and one nonlinear part. The linear part will ensure that system is in the sliding surface, and that is computed by making this dt is equal to 0. Now, if I make dt is equal to 0, x plus bu is equal to 0. So, u is equal to minus a by b into x. Clear? So, this is the part u equivalent is equal to minus a by bx. First part. This is the control law which will keep the system in the sliding surface. But if the variables go out of the sliding surface, somebody should be there to push them. That is the nonlinear control law. Nonlinear control law which will push it, it is not standardized. There are many types of nonlinear control law which are there. Usually a sign function. Sign function means if x is greater than 0, push it here. If it goes this side, push it this side. If it comes this side, push it this side. Right? So therefore, you see this is the equivalent part and this is the, and the system is this. Right? You will do an example here. Have I given the example in the program, or I think I have given that? Yes. Similarly here, you see. But that's the problem with the sliding mode controller. Because of the switching law, the response will chatter a little bit there. But that's fine. There are thousands of papers, chattering reduction, reduce the chattering, how this is reduced, so those things are there. But the important point is, it is robust. It is robust whenever in the sliding surface. That point you have to be very careful. It is not robust when you are traveling from a hostel to this room. No. There somebody can kidnap you. You don't know. So reaching phase should be as small as possible. The reaching phase should be as quick as possible. Because by that time there is no guarantee. Guarantee will be taken whenever you are in the sliding surface. Okay? Any questions? No? Yeah.
What is the chattering in sliding mode control?
Chattering means because the control law, because of nonlinear control law, see, that's the point. Again, the same analogy. You should understand the concept. Always think of the analogy. You are in this surface. Some people, chattering will come because of the nonlinear part of the control law, right? So that is one person who wants to go out of the room. So the controller, what will do? He will push him. In normal case, what you will see? He wants to go out. Then you will push him. Then he will shout or he will not shout. He will know why you are pushing me. Same system also tells the same thing. It will chatter. Got a point? I have seen, I have studied the control theory, what humans behave, the systems behave exactly the same thing. The moment you push him, then you give a large control effort, it will shout more. Hey, why you are doing like this? So the amplitude will go up. Okay, so chattering. The wording is not same thing. There will be chatter, there will be discussion, because the person is standing there, he is trying to go out, he is trying to push him, so there will be dialogue. Yeah. Any,
Optimization techniques used for this sliding motor control?
no, I have never done it. Because always we say that try to use those very simple controllers. I am against using very complex controllers. Because nowadays all these people are doing it. Sliding mode, MPC, PID, observer, all four combined together. Our people are doing it. Our people are doing it, I am telling you. I am doing it. I am doing it. Yeah, yeah. Yeah. Yeah, slide is supposed to be stable, yeah. Yeah, it will work. It has no assumption. No. Very simple. You see, the only thing that is the reaching law should be there. Plant is unstable. I am violent, but I am by the reaching condition is satisfied. Suppose I am violent, I am unstable, but the condition says that the sigma dot is less than 0. That means it is possible to reach here. So you are unstable, but you are creating disturbance, but doesn't matter. I have put you in the boss. You are coming here. You may be unstable, but you are reachable. You got a point. You are unstable, but you are reachable. You are disturbance maker, but I can take you to Mira beach. You are not, if you are a good person, that's fine. But you are a bad person, but I have got a capability. You also agree to go with the Mira beach. So I am taking you reaching phase. Reaching condition has to be satisfied. That is important. No, reaching phase has to be calculated before. Sigma dot is less than 0. I think the proof is there somewhere. One minute. I think. Sigma x is equal to x. Sigma x is equal to x. So sigma dot x dot is less than 0. That condition only is satisfied, it will not happen. Any other questions? I couldn't get it. That. It will change it because it will now behave as per the sliding surface design. No, the theory is for nonlinear system only. You see here, I can see here, this is the linear system we have defined here. So, suppose x dot is equal to x plus b is linear system, and this is the disturbance, and this disturbance you are taking sine wave. You are saying this disturbance is sine wave. No, no, I understand that. What you say coming. Sliding mode controller has to be designed. It is not a model-free controller. It is not a model-free controller. The system has to be represented by a model, either a linear model or a nonlinear model. This example here, you know that I think the assignment that is a nonlinear model is there or something like that. So what you are telling that the signal, how you model it as a XT or something like that, is it in this form? This form. So what the sine wave is there? Where? In the XT is equal to AX plus BU, what is the sine wave? AX is sine wave? AX is a sine wave. I couldn't understand how AX is a sine wave. What is the system matrix? Yeah. Yeah, you represent that thing in the state space. Then only you can apply these things. So how do you model that inverter in the state space? What is that A matrix? Yeah. Yes, that's the point. No, U of T is a noise. Huh? No, that means BU, not BU, that is, sorry. Why that? Yeah, so BU is the noise. So that your system doesn't have an input. The extra is equal to AX plus noise. Huh. 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 Oh, okay. So, so what you do in that case, I understand what I was saying. So now, you keep something BU because input has to be given. That noise which is coming, that will be represented as D zeta. Huh? No, there is no point in removing it. And also, there is no need of knowing the D also. There is no need of knowing the D. You can still design it automatically, it will filter out, sliding mode control. That is the theory. Even if there is no need of D to be known, you take the system, but you have to apply this U somewhere. You are saying that U is not there. That's you. Without U, how can do it? Yeah, U is there. Uh-huh. No, see, you are saying that this U is changing the, we will talk offline, we'll see. I'll see. Yeah? Yeah. What is talking? We'll close it.